Good evening, students. How are you all? So, welcome to the session of real numbers. This is session 5 and this is the last session of real numbers. So, we will be doing a quick revision of the same and also we'll be practicing a lot of questions today. So, real numbers, we have started a lot. We've started Euclid's division lemma. We have started the fundamental theorem of arithmetic. We've also learned the HCF and LCM and the relationship between these two. So using all these things, I have a lot of questions here today. So we'll discuss a lot of questions and these are all past year questions. So coming to the first one, write the sum of the exponents of prime factors in the prime factorization of 196. So we have 196 here. I'm going to first prime factorize it. We have to find the sum of the exponents of prime factors. So the first step is we are going to first find the prime factors. So we'll start with 2 here. As it is an even number, we are going to start with 2 and we'll get 9 here and then 8. Then this will again be divisible by 2. We are going to get 49 here. Then by 7, 7, 7 and 1. Finally, we can say 196 can be written as 2 square into 7 square. As we can see that the exponents here are 2 and 2. So we have to solve for the sum of the exponents. So sum of exponents here is 2 plus 2, that is 4. So 4 is the final answer. Sum of the exponents of the prime factors of 196 is 2 plus 2, that is 4. Alright, so let us proceed now. Find the smallest natural number by which 1200 should be multiplied so that the square root of the product is a rational number. Square root of the product should be a rational number. I'm repeating the question. Find the smallest natural number by which 1200 should be multiplied so that the square root of the product is a rational number. We are going to take here 1200 and we are going to divide this by 2. We'll get 600 here. Then divide by 2 again, we'll get 300. Then by 2 again, we are going to get 150. Okay. Then we'll divide by 2, 75. 75 is divisible by 3. We'll get 25 here. Then 5, 5 here. And again, this is divisible by 5. Finally, we have 1 here. Now for 1200, we can write this as 2 into 2 into 2 into 2 into 3 into 5 into 5. So that's 2 into 2 into 2 into 2 into 3 into 5 into 5. Now we want square root of the product as a rational number. We are looking for the square root. That means we need to make pairs. So we have this pair. This is another pair of 2. This is a pair of 5. Only 3 is not occurring in pair. That means 3 is the smallest natural number by which 1200 should be multiplied so that the square root of the product is a rational number. So you will write here, therefore 3 is the required natural number. 3 is the required natural number. That means if you multiply 3 by 1200, you are going to get 3600 and the square root of the same, that square root of 3600, that's 60 actually, is a rational number. Now coming to the next step, given that square root of 2 is irrational. This is the next question. Given that square root of 2 is irrational. This we already know, the square root of 2 is an irrational number. We have to prove 5 plus 3 root 2 is an irrational number. So similar question we did yesterday also. So here we are going to start with let if possible 5 plus 3 root 2 be a rational number. It is a rational number. Now if 5 plus 3 root 2 is a rational number, we can write this in the form of a upon b, where b is non-zero. B being a denominator is not equal to 0. I'm going to take this 5 on the other side and this will become minus 5. So we have 3 root 2 is equal to a upon b minus 5. Now we are going to take LCM here. So we'll get 3 root 2 is equal to a minus 5b upon b. Now this 3 I'm going to take on the other side and I will get root 2 is equal to a minus 5b upon 3b. So this is in the form of P upon Q. This is in the form of P upon Q. So we can say that this is a rational number. Now this is a rational number, but then we know root 2 is an irrational number. So how can a rational and an irrational number be equal? Not possible. This is a contradiction. Therefore, our assumption was wrong. Our assumption was 5 plus 3 root 2 is a rational number. It's a wrong statement. So we'll write, therefore, our assumption was wrong. That means 5 plus 3 root 2 is irrational. So we assume that it's a rational number, but then now we can conclude that it's an irrational number. Okay. I hope you've all understood this. Let us proceed. Prove that one of 3 consecutive positive integers is divisible by 3. So we are going to first write 3 consecutive positive integers. So let us denote the consecutive positive integers as n, n plus 1 and n plus 2. Now we know that every third number is divisible by 3. Every third positive integer is divisible by 3. Like we have 3, then we have 6, then 7 and 8, they are not divisible by 3. 9 is divisible by 3. Then we have 10 and 11 not divisible by 3. Then we have 12 divisible by 3, and so on. So every third positive integer is divisible by 3. Now if I take 3 consecutive positive integers as n, n plus 1 and n plus 2. Now let us say that if we have n is equal to 3q, that means n is divisible by 3, then n plus 1 and n plus 2, they will not be divisible by 3. Not possible. So out of these 3, we have n as 3q, that's divisible by 3. Now let us say that this is divisible by 3. That's the next case. That let us say that we have n is equal to 3q. 3q, that means it's a multiple of 3. It's divisible by 3. Then in that case, n and n plus 2, they won't be divisible by 3. In the same way, if we take n plus 2 as a multiple of q, as a multiple of 3, that means it's divisible by 3, then n and n plus 1, they will not be divisible by 3. So I'm repeating this question. Prove that one of every 3 consecutive positive integers is divisible by 3. So we are going to take 3 consecutive positive integers as n, n plus 1 and n plus 2. Now we have 3 cases, either n is divisible by 3 or n plus 1 is divisible by 3 or n plus 2 is divisible by 3. As I told you that every third positive integer is divisible by 3. In the first case, if we have n as a multiple of 3, then we can say n plus 1 and n plus 2, they're not divisible by 3. If we have n plus 1 as a multiple of 3, then we can say that n and n plus 2, they're not divisible by 3. And if we have n plus 2 divisible by 3, then n and n plus 1, they won't be divisible by 3. So finally, we can say that out of these 3, only one of these would be divisible by 3. I hope, children, you've understood this. Okay. Now let us proceed. Find the largest number which divides 70 and 125, leaving remainder 5 and 8 respectively. So we want a number, largest number, which divides 70 and 125, and it should leave remainder 5 and 8 respectively. That means 5 in case of 70 and 8 in case of 125. So we'll take this 70 and we are going to take reduce this by 5. So we'll take 70 minus 5, that is 65. Then we are going to take 125 minus 8. This is going to become 117. So actually, I have made this 70 and 125 exactly divisible by the largest number which I am looking for. That is why I have deducted the remainder from it. I have deducted 5. That's actually, it's leaving remainder 5 in this case. So I have deducted 5 from 70. I've got 65. Now this 65 would be exactly divisible by the largest number which I am looking for. Then we have 125. I'm going to reduce this by 8 because again 8 is the remainder in this case. It's given to us. So this will become 117. Now this 117 would also be exactly divisible by the largest number which I'm looking for. So now finally the largest number I'm going to find out which divides 65 and 117. Which divides 65 and 117 I'm saying because these two are exactly divisible by that number. Actually, I have to now solve for the HCF of 65 and 117. So, in order to solve for the HCF of 65 and 117, we are going to prime factorize these two. We'll prime factorize these two separately. So, this is going to go by 5 and we are going to get 13. 13 is a prime number. This will give us 1 here. Now, let's take this 117. This will go by 3. We'll get 3 here and then 9 here. 39 is divisible by 3. We're going to get 13 here and this is divisible by itself. So now 65 is equal to 5 into 13. 117 is equal to 3 into 3 into 13. Now, as we can see, 13 is the common factor of 65 and 117. It's the highest common factor actually. So 13 is the largest number which divides 65 and 117. So we have HCF of 65 and 117 as 13. 13 is the largest number which divides 65 and 117, or say 13 is the largest number which divides 70 and 125, leaving the remainder 5 and 80. 8, 5 and 8. Thus we can say that 13 is the required number. It's the required number. I hope children you've all understood this. Now let us proceed. Now coming to the next question. This is very simple. Can two numbers have 15 as their HCF and 175 as their LCM? Give reason. Now we want two numbers having 15 as their HCF and 175 as their LCM. We need to figure out whether such a case is possible. Now we know LCM is actually a multiple of HCF. So LCM should be exactly divisible by HCF. So let us see here whether 175 is divisible by 15. I'm going to take this 175 and I'm going to divide this by 15. Let's see. We have 15 here. Then we are left with 2, 25. This will go by 1. Then we have 15. And finally, we are left with 10 as the remainder. So we can say 175 is not divisible by 15. So it's not possible for LCM to leave remainder when we are going to divide it by the HCF. Not possible. LCM must be divisible by the HCF. But in this case, it's not. So we cannot have two numbers having 15 as their HCF and 175 as their LCM. I hope you've all understood, children. Okay. Now, coming to the next concept, check whether 15 raised to the power n can end with digit 0 for any natural number n. N belongs to n means n is a number, n denotes a number, belongs to n. This n is the set of natural numbers. We have all natural numbers here. So that this denotes that n is a natural number. So a similar question I discussed yesterday also. For a number to end with digit 0, it should have 0 it's the same thing that it should have 0 in the ones place. Now, if a number has 0 in the ones place, that means 10 must be a factor of that number. 10 must be a factor of that number. That means 2 and 5 both must be a factor of that number. I'm repeating this. I want to check whether 15 raised to the power n can end with digit 0. That means that I have to check whether it has 0 in the ones place. Now, for a number to have 0 in the ones place, it must have 10 as its factor. If 10 is a factor of that number, then 2 and 5 they must be factors of that number. So let us check whether 15 raised to the power n, it has 2 and 5 both as its factor. So I'm going to take 15 raised to the power n. I know that 15 can be written as 3 into 5 raised to the power n. That is 3 raised to the power n into 5 raised to the power n. So here I can see I have 5 as a factor of 15 raised to the power n, but I don't have 2. So therefore I can conclude that 15 raised to the power n cannot end with digit 0. 15 raised to the power n cannot end with digit 0 for any natural number n. Okay, children, let's proceed now. In this question, it is given that in a school, the duration of a period in junior section is 40 minutes and the senior section is 1 hour. So this is given in minutes and this is given in 1 hour. If the first bell for each section rings at 9 a.m., when will the two bells ring together again? So we have a school where the duration of a period in junior section is 40 minutes and in the senior section it is 1 hour. So I can write 1 hour as 60 minutes also. Now, the first bell for each section rings at 9 a.m. So both the bells are ringing together at 9 a.m. because that's the beginning of the first period. When will the two bells ring together again? So in this case, I want the bells to ring again together. I'm going to solve for the LCM of 40 minutes and 60 minutes here. So let us see. We have 40 and 60 here. We can divide this by 2. We'll get 20 here and 30 here. Then we'll divide by 2. We are going to get 10 and 15. Then by 2, we are going to get here 5. And this is not divisible by 2. We'll write 15 as it is. Now this will be divided by 3. We are going to get 5 and 5. Finally, we have 5 here. So now we are going to solve for the LCM. LCM of 40 and 60 is 2 into 2 into 2 into 3 into 5. So let us solve this. This is 2 into 2, 4. 4 into 2, 8. 8 into 3, 24. 24 into 5 will give us 120. So 120 is the LCM of 40 and 60. This means that after 120 minutes, the bells are going to ring again together. After 120 minutes means after 2 hours. So if the first bell for each section rings at 9 a.m., then the next time when they're going to ring again, it would be 11 a.m. After 120 minutes means after 2 hours. So at 11 a.m., the bells will again ring together. Now coming to the next one, it's given in the question that the HCF of 306 and 1314 is 18 and the LCM we have to find out. Now we've already discussed that the HCF of two numbers, if we take and we multiply it with LCM of those two numbers, it is same as product of the numbers. So in this case, we know the numbers. We have 306 and 1314. LCM we know it's 80. HCF we know it's 18. LCM we need to solve for, and then we know the numbers also. We have 306 into 1314. Now I'm not going to multiply this. I'll just first take 18 here and this will get divided by one of the numbers. Let's see. We have 306 into 1314 over 18. Now let's divide this by 18. 1314 divided by 18. So this will go 1 time. This will go 7 times and then 3 times. It's 73 here. Finally, we have LCM as 306 into 73. That is 22338. That is 22,338. So that's the LCM of two numbers. So in such cases, we are going to use the concept HCF of two numbers multiplied by LCM of those two numbers is same as product of the given numbers. Now this one is very simple. How many irrational numbers lie between square root of 2 and square root of 3? Write any two of them. So square root of 2 we all know it is 1.414 and then we have some numbers after that, a few digits after that. Then we have square root of 3 as 1.732. So there are infinite irrational numbers between two irrational numbers. We know square root of 2 and square root of 3, they are irrational numbers. Between two irrational numbers, we have infinite number of rational numbers. Now we have to write any two of them. Any two we can write. So we know any non-terminating, non-repeating decimal number is an irrational number. So I have to write one non-terminating, non-repeating decimal number between these two. So I can write this as 1.424224222 and so on. So it's non-terminating, non-repeating. I can also write this as 1.515115111 and so on. So these are two non-terminating, non-repeating decimals. So they are irrational numbers. Also, they lie between these two numbers. Now let us proceed. Write the HCF and LCM of smallest odd composite number and the smallest odd prime number. So this is first part of the question. We'll first solve this. We want the HCF and LCM of smallest odd composite number. Smallest odd composite number is 9 and the smallest odd prime number. Smallest odd prime number is 3. We have to write the HCF of 3 and 9. Very clearly we can say that the HCF of 3 and 9 is 3. We also have to write the LCM of the same. So LCM of 3 and 9, we know that 9 is a multiple of 3. So the LCM in this case is 9. If an now that's the next part of the question. If an odd number p divides q square, then it will divide q cube also. We have to explain this. We have an odd number p, okay, it divides q square. If it divides q square, can I write that q square is equal to pm for some integer m? Okay. Now we know that odd number p divides q square. So I can write q square as p times of something for some integer m. Then it will divide q cube also. Now let us take q cube. Q cube, I'm actually multiplying both the sides by q. I'm going to get q cube here and then I'll get pmq. Now I want to prove that p will divide q cube also. So I can write this as p times of mq, and this shows that q cube has p as one of its factor, because it can be written as p times of something, p times of m cube, which is an integer. So finally we can say that p divides q cube also. Children, I am repeating this question. We in the first part we have to write the HCF and LCM of smallest odd composite number and smallest odd prime number. Now smallest odd composite number, we know it's 9 and the smallest odd prime number is 3. HCF of these two is 3. LCM of these two, we know that 9 is a multiple of 3. So we know that the LCM is 9. In the next part, they're asking if an odd number p divides q square, then will it divide q cube also? You have to explain this. We have an odd number p, it divides q square. We know this. So we can write q square as p times of some integer m. Now we are going to multiply both the sides by q. We will get q cube and pmq. Now q cube, as we can see, can be written as p times of some integer here. So we can say that p divides q cube. P is one of the factors of q cube. So p divides q cube. I hope you've all understood this. Now let us proceed. Coming to the next question. We have a rational number. A rational number in its decimal expansion is 327.7081. So this is the decimal expansion of a given rational number. What can you say about the prime factors of q when this number is expressed in the form of p upon q? Give reason. So it's very simple. It's given to be a rational number, and also we can see that it has a terminating decimal expansion. So we've discussed this earlier also. A terminating decimal expansion if we have for a rational number, then if we write that rational number in the form of p upon q, then the prime factors of q, they're of the form 2 raised n, 5 raised m, where n and m are non-negative integers. I'm repeating this. We have a rational number. The decimal expansion of the same is given to us, and we can see that it has a terminating decimal expansion. Now they're asking us, what can you say about the prime factors of q? What can you say about this q? The prime factors of q when this number is expressed in the form of p upon q. So as we know that it has a terminating decimal expansion, then we can say that the prime factors of q, prime factorization of q, is of the form 2 raised n, 5 raised m, where n and m are non-negative integers. This means that the prime factors of q we have as 2 or 5 or both and nothing else except that. Now let's discuss the next question. what is the HCF of smallest prime number and the smallest composite number? Now the smallest prime number is 2. 2 is the smallest prime number and it is the only even prime number. It's even also, it's the only even prime number. And the smallest composite number is 4. We have to find the HCF of 2 and 4. As we know, we can very clearly see here that the HCF of 2 and 4 is 2. Because we can write 4 as 2 into 2. 2 is itself a prime number. So the HCF of 2 and 4 is 2. So finally, we have the smallest prime number 2 with the smallest composite number 4. HCF of these two is 2. Now this is an interesting question. The LCM of two numbers is 14 times their HCF. So LCM of two numbers is 14 times their HCF. The sum of LCM and HCF is 600. So we know LCM plus HCF is equal to 600. Also we know one of the numbers is 280. Find the other number. So let's say that one of the numbers here is X and the other one is Y. We know X is 280 and we have to solve for the other number. That's Y. I'm repeating this. The LCM of two numbers is 14 times their HCF. So LCM is equal to 14 times of HCF. Also we know that the sum of the LCM and HCF is 600. LCM plus HCF is 600. One of the numbers we know is 280. We have to solve for the other number. Now LCM is 14 times the HCF. So I'm going to write this as 14 times of HCF. So 14 times of HCF plus HCF is equal to 600. That is actually 15 times of the HCF we know is 600. So if we take 15 on the other side, this will get divided. So we have HCF is equal to 600 over 15 can be written as 40. If we simplify this, this will become 40. Now we know that the HCF is 40. HCF if I put here, I'm going to get the LCM. LCM is equal to 14 times of the HCF. So HCF I've got 40. I'm going to write 40 here. And finally, I'm going to get 14 into 4. That is 560. So the LCM here is 560. Now I've got the LCM. I have got the HCF also. And I know one of the numbers here is 280. I have to solve for the other numbers. So we know that HCF of two numbers if we take and if we multiply with LCM of those two numbers, it is same as product of the numbers. So in this question, we know that the HCF is 40. We know that the LCM is 560 that we've already solved here, 560. And we know that one of the numbers is 280. So X is 280. We have to solve for Y. Now I'm going to take this 280 on the other side. Let's see what do we get. 40 into 560 upon 280 equal to Y. Now 560, 280. This can be cancelled. We'll straight away get 2 here. 40 into 2 we are left with. So finally we have Y as 80. That means the other number which we are looking for is 80. Children, I'm repeating this question. Oh, I think I'll have to write this again. Okay, doesn't matter. The LCM of two numbers is 14 times the HCF. So we know that LCM is 14 times the HCF. And then we know that the sum of the LCM and HCF is 600. I'm repeating this again. So we have LCM as 14 times of HCF. We also know that the LCM and HCF, they add up to 600. Now, if I replace LCM by 14 times of HCF, I'll get 14 HCF plus HCF equal to 600. And this, when I add, I'm going to get 15 times of HCF is equal to 600. Now, 15 will go on the other side. We will get HCF is equal to 600 divided by 15, that is 40. Now, HCF we've got 40. If I pick up this 40 and I put it here, I'm going to get LCM as 14 times of 40, that is 560. 14 into 40 will give you 560. So now we know that HCF is 40 and LCM we know it is 560. Now we know HCF into LCM is product of the numbers. So HCF is 40, LCM is 560. These two we've already solved for. One of the numbers x we know is 280. We have to solve for the other number. 280 we can go on the other, we'll go on the other side, and then we will get 40 into 560 over 280. We can cancel out this, we'll get 2 here. So y is 40 into 2, that is 80. So the other number which we are looking for is 80. I hope you've now understood this. Okay. Now let us discuss the next one. Just give me 1 minute. I think there is some problem. Children, give me 2 minutes. I think there's some technical issue. Just excuse me for 2 minutes. Okay, so we were discussing this. Just let me check if this is okay. All right, just give me 2 minutes. Children, can you see the slides here? Okay. And which question we were discussing? No, not this one. This one. Yes, we were supposed to discuss this one. Just give me, yes. I hope you can see this. Identify square root of 49 over 147 as rational or irrational. Okay. All right. Now let us proceed. We have square root of 49 over 147. We need to check whether it is rational or an irrational number. So 49 can be written as 7 into 7. Let us check whether we can prime factorize this 147. We have 147. This we are going to divide by 3. We will get here 4 and then 49 again. So in fact, okay, so let's solve this if we've started like this. So this is 3 into 7 into 7. Now this 7 and 7, 7 will get cancelled, and we are left with square root of 1 upon 3. That is 1 upon square root of 3. Now here we have 1 upon square root of 3. It is an irrational number. So 1, as we've discussed earlier, if we take this as a rational number, so it will be in the form of a upon b, and then let's take reciprocals on both the sides. We are going to get square root of 3 is equal to b upon a. So square root of 3 is in the form of p by q. It's a rational number, but then that's a contradiction. We already know that square root of 3 is an irrational number. Therefore, this given number is irrational. So children, when you come across such a question, you have to first of all simplify, like whatever is possible you have to cancel out, and then whatever you're left with, then you just observe whether it is a rational number or an irrational number. Now let's discuss the next one. If a and b are co-prime numbers, then find the HCF of a and b. So we have a and b, two numbers, they're already given to be co-prime. They're given to be co-prime, that means they don't have any common factor other than 1. 1 is a factor of every number. So this a and b, they're given to be co-prime, that means they don't have any common factor other than 1. So if they only have 1 as the common factor, then the HCF of a and b would be 1 only. Because it is 1 as the only common factor, so that's the highest one also. So HCF of a and b is 1. Now find the greatest number that will divide 445, 572 and 699, leaving remainders 4, 5 and 6 respectively. So a similar question we have discussed just now also, where we were dealing with two numbers leaving remainders, like we did 70 and 125. They were leaving remainders 5 and 8. So this question is similar to that only. So we are going to first take the numbers 445. 445 leaves remainder 4. So we are going to get 441. 572 leaves remainder 5. So we will reduce this by 5. We will get 567. 699 leaves remainder 6. We are going to get 693. Now we are going to look for the greatest number that will divide 441, 567 and 693. That means we are looking for HCF of these three numbers. So let's take this 441. We'll factorize this. This will go by, let's see whether it goes by 3. We have 3 here. Then we have 147. Then this will go by 3 again. We are going to get here 449. Then 7, 7, 7 and 1. Now let's take 567. We have 567 and this is going to be divisible by 3. Let's see. We have 1 here. Then we have 8. Then we have 9. This will divide by 3. We'll get 63. This by 3. We are going to get here 21. Then by 3 again. We'll get 7, 7 and 1. Now we have 693. 693 is 3. We will get here 2, 31. Then this is divisible by 3. We are going to get 77. Then by 7 and then we have 11, 11 and 1. Okay. Now we have 441. This is the prime factorization of 441. We have 3 into 3 into 7 into 7. Then we have 567 as 3 into 3 into 3 into 3 into 7. And then we have 693. That is 3 into 3 into 7 into 11. Now we can see that 3 is a common factor here. Then we have another 3 also. That means we have 2 3s here. And then we have 1 7, another 7, another 7. Anything else? No. We have 7 here, but then we don't have any other 7 in these two. We have 2 3s, but then we don't have any other 3s. We have 11, but there are no 11s. So the common factors here, we have 3. Again, we have 1 more 3 and then 7. So finally, the HCF here would be 3 into 3 into, and we have 1 7 here. So 3 into 3 is 9. 9 into 7 will give us 63. So HCF here is 63. HCF of 441, 567 and 693 is 63. This we've already solved for. Finally, we can say that 63 is the greatest number that will divide 445, 572 and 699, leaving remainders 4, 5 and 6 respectively. 63 being the HCF of 441, 567 and 693 will exactly divide these three, but will leave remainders in case of 445, 572 and 699. So you can straight away say, therefore 63 is the required number. Have you all understood, children? Great. Now in the next question, we have 2 tankers. They contain 620 liters and 840 liters of diesel respectively. Find the maximum capacity of a container which can measure the diesel of both the tankers in exact number of times. In exact number of times. I'm repeating this question. We have 2 tankers and they contain 620 liters and 840 liters of diesel respectively. We have to find the maximum capacity of a container which can measure the diesel of both the tankers in exact number of times. That means when we are going to take the containers, there should not be anything left out. That means there should not be any remainder in this case. So we are actually looking for the HCF of 620 and 840. So we'll take this 620. We are going to divide this by 2. We'll get 310. Then this by 2, we are going to get 155. This by 5, we are going to get 31. And 31 is itself a prime number. We'll leave it. Now we have 840. We'll divide this by 2. We are going to get 420. Then by 2, we are going to get 210. Then by 2, we'll get 105. Then this by 3. This is divisible by 3. We'll get 35. Then 35 is divisible by 5. Then we have 7. Finally 1. So 620 is 2 into 2 into 5. 840 is 2 into 2 into 2 into 3 into 5 into 7. Now we are going to look for the common factors. We have 2 here. We have another 2 here. We have 2 here. We have one more 2 here. Then we have 5 here. We have another 5 here. Sorry, we have 31 also. I just missed out this 31. Okay. So now we have the HCF of 620 and 840 as 2 into 2 into 5. That is how much? 2 into 2, 4. 4 into 5, 20. So the HCF is 420. That means the maximum capacity of the container which can measure the diesel of both the tankers in exact number of times is 20 liters. Please notice when you write the concluding statement, do write 20 liters. You have to write units also. Units carry marks in the exam. Now let's discuss one more question. The decimal expansion of the rational number 43 over 2 raised to the power 4, 5 raised to the power 3 will terminate after how many places of decimal? So we have 43 upon 2 raised to the power 4 into 5 raised to the power 3. Will terminate after how many places of decimal? So we have 2 raised 4 here and we have 5 raised 3 here. I'm going to multiply this by 5 so that I get 5 raised 4. I'll have to multiply this also by 5. It's not possible to multiply something by the denominator and not multiplied by the numerator. That will actually change the value here. So 43 into 5. 43 into 5 will give us 215. And this will give us 2 raised 4 into 5 raised 4. So this can be written as 215 upon 2 into 5 raised to the power 4. So this is actually 215 upon 10 raised to the power 4. So we have 215 upon 10,000. So if I write this in decimal, I'm going to get 0.0215. So the decimal expansion of this rational number will terminate after 4 places of decimal. After 4 places of decimal. I hope you've all understood this. Now let's discuss the next one. So I think a similar one we did just now. So we'll pick up another question. If n is equal to 2 cube into 3 raised 4 into 5 raised 4 into 7, then the number of the consecutive zeros in n where n is a natural number is. So we are going to look for the number of consecutive zeros in n. We have n given to us as 2 cube into 3 raised to the power 4 into 5 raised to the power 4 into 7. If I take these two together, because 2 and 5 will give us 10, that is actually going to give me 0 in the end. So I'm going to take this 2 cube into 5 cube into 5. Please notice I've written this 5 raised to the power 4 as 5 cube into 5. And this I'm not touching, I'm just writing as it is. If I take these two together, I can write this as 2 into 5 raised to the power 3. And rest of the terms I'm writing as it is. There's no change here. Now this is 10 raised to the power 3 into 5 into 3 raised to the power 4 into 7. So whatever number we have here, that we are going to multiply by 10 raised to the power 3. So that is going to give us 3 consecutive zeros in the end. So finally, this number n will have 3 consecutive zeros in the end. We have to solve for the number of consecutive zeros in n. So that is going to give me 3 consecutive zeros in the end. I hope you've all understood this. We've just combined this 2 cube and 5 cube. This 5 raised 4, we have written as 5 cube into 5. And then we've combined these two. 2 into 5 will give us 10. So here we have 10 into 10 into 10. That's 10 cube. This 10 cube is going to give us 3 zeros in the end. So that is how we are going to get the number of the consecutive zeros. We have 3 consecutive zeros in this natural number n. Have you all understood, children? Now let's discuss one more question. The product of two numbers is 1900 and their LCM is 100. Then the HCF of the numbers is. This one is very simple. We know that the HCF of two numbers we have, and then we take the LCM of two numbers, whatever it is. either same as product of the numbers. Now, the product of the two numbers is 1900. We know that this is 1900. And the LCM is 100. We know this is 100. We have to solve for the HCF. So I'm going to replace, just right here, HCF. That's all. Now take this 100 on the other side. We will get HCF is equal to 1900 over 100. We can cancel out the zeros, and finally we will have HCF as 19. So HCF of the given numbers we have 19. Have you all understood, children? Very good. All right, children. So that's all for today. I am winding up here, and tomorrow we are going to discuss a new topic. So we are going to discuss tomorrow's second chapter, that is polynomials. Thank you, students.